to study. I decided to start studying this stuff now because the I did a brief research on the data that I want to get from Ethereum. What kind of data can I get? And it looks like for all the data that I want, I actually need to have the historical data of Ethereum entirely. And for that, I need the hardware. So I decided to start studying this stuff here before because I'm playing poker off stream to get the money to pay for the hardware. And once I have the hardware, then I go back to extracting the data. And I might go back and continue to study Rust because I want to understand the source code of the polars, which is a Python library for reading data frames that makes the data frame not the data frame, but makes it reading from the data frame a lot faster and uses less memory. And I'm interested in that, obviously. So I think that was the main point why I started to use Rust in the first place. So I might study that today as well. But I wanna study the Uniswap V3 paper again, and I wanna study maybe Ethereum yellow paper. Go back to this smart contract hacks articles that I read some time ago. Then read this again, which is a series of articles that I read twice now, which explain how the EVM reads the contracts and parses into some kind of assembly, some variation of assembly. And I also want to read these articles here about zero knowledge proof, which is a thing that is used to make layer 2s on the Ethereum network, which is basically a method that allows you to verify something without telling anything about what you're verifying. So people use that to create a bunch of transactions off chain and use different ways to do that. Polygon uses a different blockchain, which is proof of stake, I think. And then they create this zero knowledge proof, then make a bunch of transactions off chain, and then at the end they do the zero knowledge proof again on the Ethereum network, and that's how it works. That's why it's built on top of Ethereum. And there's several, not several, I think there's two main different variations of zero knowledge proof that I saw so far. One is the optimistic rollup, the other is some zero knowledge proof, I think, or something like that. Zero knowledge rollups. And there's also two different ways of zero knowledge proofs. One is interactive and the other is not interactive. In the interactive one, there's a sequence of transactions between two different agents, and then that is used to verify if whatever the first agent did is correct, as far as I understand. So it's basically a mechanism that allows you to prove something without having to say anything about it, which allows privacy and allows to scale. Which also means that you probably can't get data from Polygon unless you have some type of deal, I think, with because I saw that you can get from Google BigQuery, but I'm not sure how they get it. And I think that proof of stake works basically whoever has tokens has the voting rights and also mines. So maybe that's one way to get information from Polygon as well. But I don't think just with RPC methods you can get it. And that's also another thing that I want to study is figure out how can I read on the blockchain the entry points of the zero knowledge proof from the Polygon. When it starts the zero knowledge proof and after all the transactions, how is put in the Ethereum blockchain again. Because as far as I understand now, that's how it works. And what else? And maybe I'll read the yellow paper as well at some point. If I have time, which I probably won't have, but I think I'll continue to study this up until tomorrow or maybe even later, depending on how long it goes. And I also think I'm considering whether or not I should just go back to this and try to just submit the challenges so I can unlock the other ones because I'm interested in this building a DAX challenge and also on this oracles challenge because I think it's going to be very helpful to understand a bunch of stuff about solidity and blockchain by doing these challenges. And also this is connected with Solidity design patterns that I also want to become better at because I know there are several design patterns, and I think it's crucial if you're gonna develop in Solidity to know them because it allows you. Some of them I think allows you to update the code in the contracts or in the decentralized application without having to redeploy the contracts constantly by using something that is called a proxy contract, which is a contract that is connected to other contracts that you use as a routing point. And then the only thing that you have to do is modify the proxy contract to call a different contract once you want to update the decentralized application. And it seems more efficient, but the downside is that it increases risk because of these hacks here, which a lot of them come from contracts calling external contracts and the problem with the fallback functions. The fallback functions are functions that are automatically called if you call a contract and the function fails. So there is a fallback, and that fallback you can put some code and then you can use to do the reentrancy attack, which is changing the state or if you draw in balance from one contract by having the fallback function, depending on. I'll read this again. I don't remember really well, but yeah, something like that. So I think I'm gonna read a little bit out loud until I get tired. Then I'm gonna listen to music and read everything quietly. And then once I'm tired, I might take a break and go back, or I'm just gonna watch these videos here. So yeah, automated market makers are agents that pool liquidity and make it available to traders according to an algorithm. Constant function market makers, a broad class of AMAs of which Uniswap is a member, have seen widespread use in the context of decentralized finance, where they are typically implemented as smart contracts that trade tokens on a permissionless blockchain. CFMMs, as they are implemented today, are often kept inefficient. The constant product market maker formula used by Uniswap V1 and V2, only a fraction of the assets in the pool were available at a given price. This is inefficient, particularly when assets are expected to trade close to a particular price at all times. Prior attempts to address this capital inefficiency issue, such as Curve 3 and Yield Space 4, have involved building pools that use different functions to describe the relation between reserves. This requires all liquidity providers in the given pool to adhere to a single formula and could result in liquidity fragmentation if liquidity providers want to provide liquidity within different price ranges. This paper represents Uniswap v3, a novel AMM that gives liquidity providers more control over the price ranges in which their capital is used, with limited effects on liquidity fragmentation and gas inefficiency. This design does not depend on any shared assumption about the price behavior of the tokens. Uniswap v3 is based on the same constant product reserves curve as earlier versions, but offers several significant new features. Another thing that I'm thinking about doing is creating arbitrage trading bots on the Polygon network from the decentralized exchanges that I have here the list. But I think I think I'm gonna after I study Uniswap and I understand better because I saw that Uniswap has an address for Polygon, and I think it works if I wanna create the bot on Uniswap to trade on Uniswap, but only on the coins that exist on the Polygon network, if that makes sense. Because of the gas fees, obviously, I wanna create one just to learn, and I don't wanna spend money. Uh, Obviously, I'm gonna have to spend money because of the transactions, but the least amount of money possibly. And I think that's gonna be interesting. And I also have the Uniswap project here. I downloaded all the projects from Uniswap and it wasn't working, so I had to put this for the linting, which because my system is Windows 64 and they didn't program for that, it was giving me a bunch of mistakes, and I also had to change the CLI. I think is this file, which is their binary doesn't capture Windows 64 for whatever reason. It gives an error if you use bin because bin becomes no, and this is pulling from the index file here, and it doesn't have the information for Windows 64, I think. I was thinking about whether or not to do a pull request, but yeah, I'm not sure. I might do that, but I'm not sure because it's gonna be some work, and I'm not sure if what I did here is the best. Well, basically, what I did was get the path here, path join, because I saw that the file that they're using is the relay.x, which is each system they have a binary that is gonna enable the CLI, and I just manually put the path here. What I would have done if in case I'm gonna do a pull request, what I'm gonna do is put else if and then put just process.platform means 64 and not put this as well, and then just put the path that I put here, and this seems to work fine. So after that I fixed that, then I had the other problem and I fixed that as well. But there's a bunch of different projects. This is the interface. I think I'm gonna play around with the interface to see how it works and look at the files and try to understand how they designed this, because there are a lot of interesting things from what I've seen here already. One is the Cypress, which is a testing library, which I never use because I'm not used to doing tests. The other stuff is this ESLint thing, which is something used to standardize the way that people write code, and I think is very useful in team projects. But I hate it using because it gives a bunch of annoying warnings, and they're not really necessary when you're coding by yourself. But maybe I should use this at some point. And the other extremely interesting thing that I saw was about analytics here. That I have something that I think is from Google Analytics, and it's called Amplitude Analytics, and that's how they track the data from users, which was something that I was talking about previously that I was gonna study at some point. So I think this is gonna be a very good way to study that. And obviously, ideally, I wouldn't want to choose something from Google because I don't want to be dependent on them. But I think, given the laws of the nature of markets, that's everyone's kind of forced on this position because of the prisoner's dilemma and the Nash equilibrium that forces everyone to be as competitive as possible, and then leads to this exponential distribution of power, which is the problem of the market economy and the exponential attack that we are seeing. But yeah, there's nothing I can do about that right now. So I think I'm gonna end up having to use this kind of stuff in my projects until I make enough money so I don't rely on anyone, and then I can start focusing on trying to create a system that is better than this, that doesn't force everyone in this position of doing things that are not necessarily aligned with the overall distribution of power, optimal distribution of power across social structures. Yeah, but it looks like it's a React app, and I'm not sure actually if it's a React app or Next.js because it has the pages structure here, but I think it's a React app and it only has the pages structure for the design. Is not because as I was looking here from the app file, which is probably definitely the main file actually, it doesn't look like they have the structure from Next.js, so I think that this is a React app only. And it doesn't look like they use APIs as well, the serverless functions from Next.js, so I'm assuming it is a React app. And the only downside of studying this is obviously that there's a shit ton of files here. This is gonna be difficult, but I think it's gonna be interesting because I can run this. I already tested. I can run, and I can see the user interface, and then I can change code here and explore the same way that I did with the NFT marketplace Silo network. And I think I'm gonna learn a lot by doing this. And this is just the interface. Then we have the V2 core, which I think is the main package of smart contracts from the functionality of Uniswap V2. And here I have the swap router contracts, which I'm not really sure what they are, but I think it's for the contracts that are responsible for the trading. These are probably responsible for setting up the liquidity and the fees and stuff like that. So I'm really interested in studying them as well. And then I have the V3 stuff as well, which I think I want to study. I'm probably not gonna have time today, but maybe I will, and then I'll study that. If not next time, I'll probably study that on stream. the main challenge of building the arbitrage bot is the math, which is a little bit annoying. It's not that hard, but it is annoying to figure out. And the math to actually get the quantity, the depth of the trade is actually really hard. And that's going to be a very big challenge, so I might not be able to do that, but I want to do at least a simple version so I understand the mechanics of it. And maybe I'll try to do it in Rust as well, because Rust is faster, so I think it's going to be better to do it in Rust. But I'm not sure if I'm gonna stream that part, because obviously in case I end up being something that makes me money, then if I share with everyone, then nobody makes money. So it's better should just do it off stream. But maybe I can do the beginning, the simple version on stream, and then if I decide to work more on that and go into the more complex mathematics and figure out ways to solve that, then I'll do it off stream. Concentrated liquidity. Liquidity providers, LPs, are given the ability to concentrate their liquidity by bounding it within an arbitrary price range. This improves the pool's capital efficiency, allows the LP to approximate their preferred reserves curve, while still being efficiently aggregated with the rest of the pool. We describe this feature in Section 2 and its implementation in Section 6. Flexible fees. The swap fee is no longer locked at 0.3%. Okay. I think I'm going to write this down. Swap fee. Eu put Uniswap feature. Was locked at. Since I already read this once and I read the other articles, I think it's going to be easier to understand. It's still quite hard because it's very complex, but hopefully this time, because I remember first time I read this, I didn't understand really well. So maybe this time, hopefully, I can get it. Where the fee tier for each pool of which there can be multiple asset pair, of which there can be multiple per asset pair, is set on initialization. The initialized supported fee tiers are 0.05%, 0.03%, and 1%. Unit governance is able to add additional values to this set. Flexible fees. Set on initialization. From 0.05%, 0.3%, 1%. I'm gonna save this. Uniswap v3 info. Protocol fee governance. Unit governance has more flexibility in setting the fraction of swap fees collected by the protocol. Improved price oracle. Uniswap v3 provides a way for users to query recent price accumulator values, thus avoiding the need to checkpoint the accumulator value at the exact beginning and end of the period for which a TWAP is being measured. TWAP, if I remember correctly, is something to do about the volume and the time that it takes, something like that. Also, I'm gonna study decentralized governance, DAOs, decentralized application governance, I think is the acronym. I already took a look at these contracts here, which are from a tutorial from DEP University about creating a simple DAO, and I'm interested to see and to understand more how something like the Uniswap, for example, how exactly this works out, who opens the votes, how does the votes work. It's kind of is a little bit weird, I'd say, how it works. Like, how is it possible that something that there's no one implicitly being in control, you can have the coordination and stuff. So, and how do you split things between the marketing team, the developer team, and everything else? How is that decided? How are the things run? Is a little bit vague for me, and I think it's a little bit hard to understand. So I'm gonna try to understand that as well. Liquidity oracle. The contracts expose a time-weighted average liquidity oracle. Yeah, time-weighted average. Wow. Time-weighted average price. Yeah. Okay. Uniswap v3 core contracts are non-upgradable by design. So Uniswap v3 is implemented as an entirely new set of contracts available here. Okay, so the V2, they apparently didn't use proxy contracts like I was talking about. The Uniswap v3 core contracts are also non-upgradable, with some parameters controlled by governance as described in section 4. So I guess this is a design pattern thing, where if you have proxy contracts, but maybe you can combine two. I think you can combine both, the governance and the proxy contracts. I don't see why you wouldn't. It's just that they decided to not implement proxy, probably because it's higher risk, if I would guess, or maybe just a personal thing, personal preference thing, kind of thing. Concentrated liquidity. The defining idea of Uniswap v3 is that of concentrated liquidity. Liquidity bounded within some price range. In earlier versions, liquidity was distributed uniformly along the x times y equals k reserves curve, where x and y are the respective reserves of two assets x and y, and k is a constant. In other words, earlier versions were designed to provide liquidity across the entire price range. This is simple to implement and allows liquidity to be efficiently aggregated, but means that much of the assets held in a pool were never touched. Having considered this, it seems reasonable to allow LPs to constrain their liquidity to smaller ranges than 0 to infinity. We call liquidity constrained to a finite range a position. A position only needs to maintain enough reserves to support trading within its range, and therefore can act like a constant product pool with larger reserves. We call this the virtual reserves within that range. This is the part that is really confusing to understand. So I understand that you are providing a smaller space for people to allow to put the ranges, because that uses the money in a more efficient way instead of wasting the range from amounts that are not actually traded enough. But this complicates things a lot, because now you can have all sorts of things where people maybe try to manipulate the price, or maybe the pool is small and then it makes the price fluctuate too much, and then it goes out of the range, and then the amount of liquidity available varies in a lot more chaotic way, let's say. So it's kind of difficult to envision how this exactly works in practice, and also to understand this graph here. Simulation of virtual liquidity. Specifically, a position only needs to hold enough of asset X to cover price movement to its upper bound, because upwards price movement corresponds to depletion of the X reserves. Similarly, it only needs to hold enough of asset Y to cover price movement to its lower bound. Depicts the relationship of our position on a range. So this one. And the current price. X real and Y real denote the position's real reserves. So this is the amount that it really has, I guess. And this C is the price, B is the amount of reserves on the Y, relative to X, the total, I think. And then A the other way around. Amount of the real distribution of the reserve is between A and B. So the total amount would be the whole graph, but the virtual reserves are from A to B. Yeah, but here it's saying virtual reserves for the entire thing, so I'm not really sure. For position on range, P, PB, and the current price, PC. Okay, so that's the range and the price is PC. X real and Y real denote the position's real reserves. X real and Y real. When the price exits a position's range, the position's liquidity is no longer active. And no longer earns fees. At that point, its liquidity is composed entirely of a single asset, because the reserves of the other asset must have been entirely depleted. If the price ever re-enters the range, the liquidity becomes active again. So it's basically it stops allowing people to trade, I think, because it's considered as zero. So it's pretty much assuming that the price is never gonna go up or down that range, I guess. But I think that's for any specific person. I think that's why it works. Now I think I get it. Because let's say you have the dollar fluctuating between 0.99 and 1.01. So you can limit your price for 0.98 to 1.02. And then if for any reason the price was gonna fluctuate more than that, then your portion of the investment starts being active and stop earning the fees. But then when it comes back again, then you start earning again. So I guess what happens is that most people are probably providing liquidity in the range that they're considered uh, tradable, let's say, given the history of the price movement for that specific coin. But that obviously is harder because there's a lot of volatility and you can predict the market. So the coins can go out of the range a lot. But in that case, the coin price would adjust. So it pretty much says that whenever there's volatility on the market and a lot of volatility, there's a huge opportunity for arbitrage because the most overall amount of liquidity in the pool is going to be capped by the investors. So the investors need to be very active when putting the price ranges so that they hedge themselves against strong movements that go beyond outside of the range. And I think that probably what's going to happen is going to follow the 80 to 20% rule, where 80% of the people are going to put the range inside of something that is closely close to the historical price of the market, and then 20% are going to have a wider range. So it's going to have, maybe it's going to follow a normal probabilistic distribution instead of the Pareto one. But I think that that's how it kind of works, if I'm understanding correctly. And then if there's a lot of volatility, the market updates for that, but then it's going to take time, I think. And in that gap of time, then it probably opens up the space for arbitrage, because even though the price can't fluctuate outside of the range, you're going to have the actual market price outside of the DAX that is going to fluctuate. So what people are going to do is just keep selling or buying that coin through outside markets and make money off that. And then if the investors don't set up the range or readjust the range, then they lose money. But I'm not really sure if that's how it works or if I'm understanding incorrectly. The amount of liquidity provided can be measured by the value L, which is equal to square root of K. The real reserves of a position are described by the curve. Okay. This curve is a translation of formula 2.1 such that the position is solvent exactly within its range. Virtual reserves, real reserves. Yeah, so I think I understand. Real reserves is the amount that is actually on the fund, on the pool. And then the virtual reserves is the extrapolation of that in order to virtually increase the liquidity so that the price fluctuates less, I think. That's what they done. And then the virtual reserves is determined by the overall amount of ranges that the pool has, I think. So each investor is gonna have this curve depending on, or maybe the whole pool has the overall curve, and then each investor has its own curve inside of this curve that follows the same pattern. So it pretty much converges into the integer for all the investors into this one, I think. So the price never goes up this point or below this point because it fluctuates. And well, as soon as it's gonna go, then the liquidity decreases to zero. I think that's the reason why. Yeah, but it's still I think susceptible for the thing that I just talked about. Because even though the price is never gonna go over this point because there's zero liquidity, you can trade with external markets if there's a big enough fluctuation, I think. Because on the other markets, then you wouldn't be bounded by this distribution here, and then you would have a bigger price or smaller, depending on which one you're looking at. I remember I was trying last time to understand this formula here. So L is the liquidity provider, which is equal to square root of K. And this part, I don't remember. So L divided by square root of K of P, price B. So I guess this is equal to C. But then it would have to be minus, not plus. I don't understand the formula really well. Y plus L times PA. The square root of PA. I'm not sure if I get it. Well, obviously, I could distribute this and then see if I multiply each one and then take the square root and see what happens. This has to be equal to K, right? Because this is L to the power of 2. So K is equals this. I assume K is a constant. Oh, so the real reserves here are this curve here. So maybe so the virtual reserves are just x times y, I think, because they didn't mention anything else. Yeah, that's probably what's going on here. and then they derive that to get to the. I think I understand. I don't understand the derivation. I think I would need pen and paper probably to come up with this, but I think this is what's happening here, where this virtual reserve curve is equal to this formula, and then if you want to get the real one, you go from this into this based on getting the square root of this. But I'm not really sure if that's the case. Yeah, it has to be because here says that the liquidity provided is equal to the square root of k. So, yeah, I think they go the other way around. They take the L, which is square root of k, and then see the virtual reserves based on that. But it doesn't matter anyway, obviously, because they're equal. And so I guess that this is the movement from this one to this one. That's the thing. So y plus L, which is would be this distance here. So from this point here until here. That's y plus L square root of PA, I assume. And the other one is, yeah, but that doesn't make sense. Oh, maybe it does actually. Yeah, I'm not gonna spend too much time on this, but I think that's what's happening here. This equation demonstrates this movement here from this and up to this curve. Yeah, when you have this curve and you translate it so that you, oh, I get it. Yeah, because the range has to be 0. So in these points here. So they're taking the initial equation here and then translating that into the range. And this range, I think, is arbitrary depending on the person. That's the difference. So each person decides when what size of the range in relationship to the virtual reserves they're gonna make it available. I think I get it now. Liquidity providers are free to create as many positions as they see fit, each on its own price range. Yeah, that's exactly what's going on, I think. Free to create as many positions as they see fit, each on its own price range. This way, LPs can approximate any desired distribution of liquidity on the price space. Moreover, this serves as a mechanism to let the market decide where liquidity should be allocated. Rational LPs can reduce their capital costs by concentrating their liquidity in a narrow band around the current price. Capital costs by concentrating their liquidity. And adding or removing tokens as the price moves to keep their liquidity active. Yeah, which was what I was saying, but in the delay they can lose money, I think, especially in volatile markets. But I think, yeah, maybe. Yeah, okay. Range orders. Positions on very small ranges act similarly to limit orders. If the range is crossed, the position flips from being composed entirely of one asset to being composed entirely of the other asset, plus accrued fees. There are two differences between this range order and a traditional limit order. There's a limit to how narrow a position's range can be. While the price is within that range, the limit order might be partially executed. When a position has been crossed, it needs to be withdrawn. If it is not, and the price crosses back across that range, the position will be traded back, effectively reversing the trade. Let me read this again. Positions on very small ranges act similarly to limit orders. If the range is crossed, the position flips from being composed entirely of one asset to being composed entirely of the other asset, plus accrued fees. I think I get that. Okay, so it works as a limit order. There are two main differences between range order and traditional limit order. There is a limit to how narrow a position range can be. While the price is within the range, the limit order might be partially executed. Oh, I understand. So instead of being a fixed point on the graph, it is a range, but the mechanism is the same. So if I put a very small range of liquidity, of providing liquidity, is like you're placing a limit order because, oh, I understand. Because once the price fluctuates, then you just traded one token for the other, but you move out of the liquidity because the range stopped. But the difference is that the range can never be small enough to be the same as in an order book where you can offer a fixed amount and then the person is gonna buy or not. But it's similar in the sense that the more money you have, the higher the range has to be because there isn't enough liquidity. So if you provide a large order in a order book, then you might lose money because as the price moves to fill the gap, then you you gain less and less for the asset. I think it's the same mechanism that is working here. Position has been crossed, it needs to be withdrawn if it is not, and the price crosses back across that range, the position will be traded back, effectively reversing the trade. Well, this part actually, the reversion there I didn't understand. When the position has been crossed, it needs to be withdrawn. If it's not, oh yeah, that makes sense. So because if the price gets into the range that you place, you're gonna trade one asset for the other, and then the price is gonna move out of the range. But if you don't withdraw that liquidity, then the price is just gonna fluctuate back, and then it reverses the position you had because it's just gonna use your liquidity again. That's what's saying there, I think. So if we choose a single position, a collection of custom positions. Okay. Example, liquidity distributions. Architectural changes. Uniswap 3 makes a number of architectural changes, some of which are necessitated by the inclusion of concentrated liquidity, and some of which are independent improvements. Multiple pools per pair. In Uniswap V1 and V2, every pair of tokens corresponds to a single liquidity pool, which applies a uniform fee of 0.3% to all swaps. While this default fee tier historically worked well enough for many tokens, it is likely too high for some pools, such as pools between two stablecoins, and too low for others, such as pools that include high volatility or rarely traded tokens. Uniswap V3 introduces multiple pools for each pair of token, each with a different swap fee. All pools are created by the same factory contract. The factory contract initially allows pools to be created at 3 fee tiers. Additional fee tiers can be enabled by uni-governance. Non-fungible liquidity. Non-compounding fees. Fees earned in earlier versions were continuously deposited in the pool as liquidity. This meant that liquidity in the pool would grow over time, even without explicit deposits, and that fee earnings compounded. Let me read this again. Fees earned in earlier versions were continuously deposited in the pool as liquidity. Oh, so the fees were redeposited in the pool. Okay. This meant that liquidity in the pool would grow over time even without explicit deposits, and that fee earnings compounded. In Uniswap v3, due to the non-fungible nature of positions, this is no longer possible. Instead, fee earnings are stored separately and held as the tokens in which the fees are paid. Non-fungible nature of positions. I'm not sure if I understand this concept. I guess in Uniswap V2, what was used to happen is that when you when you pay for liquidity, when you deposit the liquidity, you can change your position between different pools. I don't get this part really well. This one I get. So they used to reinvest the fees into the pool, so it grows automatically. But this one I don't understand. Oh, I guess it's because when people trade, the fees associated with that trade are not part of the pool anymore. That's what this is saying. It's kind of confusing. Instead, fee earnings are stored separately and held as a token in which the fees are paid. Oh, I guess it's because it changes the relationship between the two tokens that are being traded. Because you have these ranges and this liquidity, virtual reserves. So you can't, because the distribution might be different, I think. That's why it's saying that it's non-fungible. Non-fungible pretty much means that you can't trade it. This is like trying to trade a cat for a cow, for example. It's not the same thing. And money is fungible because it's a currency, so you can quantify and change. And is the difference between NFTs and tokens, for example. NFTs are not fungible because you can't, they are unique. But this relationship between the two, I don't understand really well. Maybe I have to go back to V2 sometime to understand that, then come back here later. I might do that today if I have time. I think, yeah, maybe it's not gonna take as much time to go through all these articles as I was thinking. But it depends. It's very, I can't really put some a time, specific time, because there I might find something that gets me into a rabbit hole and then it complicates things a lot. So Uniswap v3 do should not function. Okay, read that. Removal of native liquidity tokens. Uniswap v1 and v2, the pool contract is also an ERC20 token contract, whose tokens represent liquidity held in the pool. While this is convenient, it actually sits uneasily with the Uniswap v2 philosophy that anything that does not need to be in the core contracts should be in the periphery, and blessing one canonical ERC20 implementation discouraged the creation of improved ERC20 token wrappers. And blessing one canonical improved ERC20 token wrappers. Arguably, the ERC20 token implementation should have been in the periphery as a wrapper on a single liquidity position in the core contract. I don't understand what this means. Also, I think I get it. So the ERC20 token implementation, which is the token for Uniswap, should be outside on the periphery. You have the core contracts and the periphery supplements the core contracts. So it's saying that the implementation should be on the periphery and be wrapped around the liquidity position in the core contract. So it's a similar mechanism from decorators in Python, where you wrap a function inside another function. That's the principle here, I think they are saying. So you should, instead of, so the way they did it, I think, was to implement the token on the core contract. And they're saying that instead of that, they should have something like a decorator, which is goes on the periphery and then it wraps around the main thing, according to the visual philosophy. but I'm not really sure if that's the case or not. The changes made in Uniswap v3 forced this issue by making completely fungible liquidity tokens impossible. The changes made in Uniswap v3 forced this issue by making completely fungible. Due to the custom liquidity provision feature, fees are now collected and held by the pool as individual tokens, rather than automatically reinvested as liquidity in the pool. As a result, in V3, the pool contract does not implement the ERC20 standard. Anyone can create an ERC20 token contract in the periphery that makes a liquidity position more fungible. But it will have to have additional logic to handle distribution of or reinvestment of collected fees. Alternatively, anyone could create a periphery contract that wraps an individual liquidity position, including collected fees, in an ERC71 non-fungible token. Hmm. So I guess they're saying that the Uniswap tokens on V2 were ERC20, which are the standard for creating tokens in Ethereum. And then in V3, there are actually NFTs, which is ERC721, I think, for creating non-fungible tokens. So they changed from fungible to non-fungible. And that's why you can't reinvest the fees because each one is unique, if I understand correctly. Yeah, ERC 721 is the NFT. So they're pretty much NFTs now instead of tokens. And I guess this is referring to the Uniswap pool, which is the because as far as I understand, when you're gonna deposit in the Uniswap, you trade the tokens ERC20 for the Uniswap tokens, I think. So before it was like you're trading through ERC20, but now is you're trading ERC20 for the NFT. You're essentially minting NFTs when you buy. And that's the reason why the fees can't be reinvested because it's not fungible anymore. And then they're explaining that you need more logic to handle that because of this. And they're saying that you can create the 20 on the periphery and make it more fungible, but then you have to handle this the distribution and investment of the fees because as your tokens get traded, then it's going to generate the non-fungible, I think, from Uniswap. And then it's up to you to decide how those extra non-fungibles that come from the fees are going to be invested, I think. That's probably what's going on. It's kind of hard to really know if that's what's going on. I guess I have to go back to the other ones, to Vichu, and read the Vichu paper to understand. Because it seems that's what I'm missing here. Governance. The factory has an owner, which is initially controlled by Uni token holders. The owner does not have the ability to halt the operation of any of the car contracts. As in Uniswap v2, Uniswap v3 has a protocol fee that can be turned on by Uni governance. Uniswap v3, Uni governance has more flexibility in choosing the fraction of swap fees that go to the protocol, and is able to choose any fraction 1 divided by n, where n between 4 and 10, or 0. This parameter can be set on a per pool basis. Uni governance also has the ability to add additional fee tiers. When it adds a new fee tier, it can also define the tick spacing corresponding to that fee tier. Once a fee tier is added to the factory, it cannot be removed, and the tick spacing cannot be changed. The initial features and tick spacing supported are 0.05% with a tick spacing of 10, approximately 0.10% between initializable ticks. 0.3% with a tick of 60, approximately 0.6%, and 1% with spacing of 200, approximately 2.02%. Finally, unique governance has the power to transfer ownership to another address. Oh, so it's kind of like a public company where the shareholders can decide. Basically, whoever has more shares is the owner because they're gonna transfer ownership to them. I think, or maybe they will decide to keep the same owner, but I don't see why. Oracle upgrades. Uniswap v3 includes three significant changes to the time-weighted average price, Oracle, that was introduced by Uniswap v2. Most significantly, Uniswap v3 removes the need for users of the Oracle to track previous values of the accumulators externally. Uniswap v2 requires users to checkpoint the accumulator value at both the beginning and the end of the time period for which they wanted to compute a TWAP. Uniswap v3 brings the accumulator checkpoints into core, allowing external contracts to compute on-chain TWAPs over recent periods without storing checkpoints of the accumulator value. Another change is that instead of accumulating the sum of prices, allowing users to compute the arithmetic mean TWAP, Uniswap v3 tracks the sum of log prices, allowing users to compute the geometric mean TWAP. Finally, Uniswap v3 adds a liquidity accumulator that is tracked alongside the price accumulator, which accumulates 1 divided by L for each second. This liquidity accumulator is useful for external contracts that want to implement liquidity mining on top of Uniswap v3. It can also be used by other contracts to inform a decision on which of the pools corresponding to a pair, see section 3.1, will have the most reliable T1. Yeah, this one I'm gonna go back, I think. I'm not sure, I think this is enough. But maybe, yeah, if I have time, I'll go back because I think I'm understanding a lot now. Probably understand more when I go through the project as well. Arc observations. As in Uniswap v2, Uniswap v3 tracks a running accumulator of the price at the beginning of each block, multiplied by the number of seconds since the last block. A pool in Uniswap v2 stores only the most recent value of this price accumulator, that is, the value as of the last block in which a swap occurred. When computing average prices in Uniswap v2, it is the responsibility of the external caller to provide the previous value of the price accumulator. With many users, each will have to provide their own methodology for checkpointing previous values of the accumulator or coordinate on a shared method to reduce costs. And there is no way to guarantee that every block in which the pool is touched will be reflected in the accumulator. In Uniswap v3, the pool stores a list of previous values for the price accumulator, as well as the liquidity accumulator described in section 5.3. It does this by automatically checkpointing the accumulator value every time the pool is touched for the first time in a block, cycling through an array where the oldest checkpoint is eventually overwritten by a new one, similar to a circular buffer. While this array initially only has room for a single checkpoint, anyone can initialize additional storage slots to lengthen the array, extending to as many as 65,536 checkpoints. This imposes the one-time gas cost of initializing additional storage slots for this array on whoever wants the pair to checkpoint more slots. The pool exposes the array of past observations to users, as well as a convenience function for finding the interpolated accumulator value at any historical timestamp within the checkpoint period. Did I read this stuff? I think I did. Yeah, I did. I think here starts getting confusing as well. And there's already a bunch of things in my mind. I'm noticing that I'm starting to deviate my concentration because I'm thinking about a bunch of other stuff. So maybe I'll take a break soon. I think maybe when I reach page 6, I'll do a meditation to take a break and then come back. I think the second part of this is gonna be harder because there's all the formulas and I'm gonna have to think about it. Might have to go back to the V2 as well to understand the TWAP better. I think I might do that actually because there might be diminishing returns for me to read the rest without understanding this because then I would probably have to read it again. But it depends on how big the white paper is. There's a lot of stuff. Oh, the technical white paper. I think I'm only gonna read the white paper and read it briefly. I'm gonna read this quietly because I read faster and reading out loud is better for concentrating, but reading quietly is better for reading faster. And I don't, it's not really important to pay attention to this stuff. I just wanna see if I can get to the point where they're gonna talk about the stuff on the V3. Hmm. So you can use ETH as a router. That's probably what this thing is about here. Swap router contracts. It's probably the code for this stuff, which is very interesting. The oracles I think I understand is Chainlink. Uh, Chainlink is an oracle as far as I understand. It basically listens to events on the blockchain and then emits these events, I think. Oh, I guess I understand what's going on now. So in order to prevent from people manipulating the price by moving the liquidity They are using the oracles which accumulate the history of the price in other contracts and during a time span, and then that's the time weighted average of Uniswap prices across a time interval. Manipulation resistance on price chain fees, chain price feeds. I wonder how they do that though, because it seems to me that it is something that is very difficult to do without running the risk of being hacked, but I'm not sure because they probably thought about this a lot. Because which oracle are you gonna use? How are you gonna get the data? Don't understand. And how are you gonna store the data on the contract? Maybe I should write this stuff because when I'm gonna study the project itself, I can look for these things. On-chain price fees are a critical component for many decentralized financial clients, including those similar to derivatives, lending, margin trading, prediction markets, and more. Despite closely tracking the real-world price, most of the time, Uniswap 1 cannot be used safely as a price oracle because the price can move significantly in a short period of time. Uniswap 2, damn, so many times. An analysis, interesting. I think I'm gonna download this for later. This one is really big. Maybe I have it already because I remember downloading a bunch of this and putting on the docs. Yeah, I have this paper, I think. Yeah, I read this paper already. Interesting. This math here is the one that I was talking about that is hard to implement. And the thing is that this paper specifically doesn't explain really well. That's why it's hard because there are things here that are not really clear on what they're doing. And apparently they're using Viper instead of Solidity. I think I'm gonna download this anyway because there might be stuff here that I don't I didn't download. Yeah, it's probably this one here in the swap analysis. Well, whatever. Don't lose anything by. Yeah, and this guy here, I remember his name. So VT includes a number of improvements for price feeds but built on top of it. First, every pair measures but does not store the market price at the beginning of each block before any trades take place. This price is expensive to manipulate because it was set by the last transaction in the previous block. So V2 includes a number of improvements for price feeds built on top of it. First, every pair measures but does not store the market price at the beginning of each block. Okay. So at the beginning of each block, it measures the price of each coin that is trading. I think I already wrote it down here. How do they do that? Maybe I should write launch measure price of each ERC20 token until the beginning. I think the difference between the V2 and V3 is that V3 stores and measures at the beginning of the blocks, but also stores for historical data, as they were saying there. This price is expensive to manipulate because it was set by the last transaction in the previous block. To set the measured price to one that is out of sync with the global market price, an attacker has to make a bad trade at the end of a previous block. Set the measured price to the global market, typically with no guarantee that they will be able to arbitrage it back in the next block. Attackers will lose money to arbitrageurs unless they can selfishly mine 2 blocks in a row. This type of attack presents a number of challenges and has not been observed to date. So I guess this is the bandit attack or something like that. Automating attack analysis on blockchain, in effect, incentive mechanisms with deep reinforcement learning. Yeah, that sounds interesting. Definitely gonna download this one as well. Attack analysis on blockchain, incentive mechanisms for deep reinforcement learning. And these people are really intelligent. It's impressive. They probably put a lot of work as well into this on a thing. Yeah, I'm definitely gonna read this one. But this one, I think I'm probably gonna read quietly because I'm gonna be tired already. Maybe I'll read some other day. To set the measured price to one that is out of sync, I think I read that. This alone is not enough. If significant value settles based on the price resulting from this mechanism, then the profit of an attack likely can outweigh the loss. If significant value settles based on the price. I'm not sure if this is the same mechanism of the bandit attack, but I think it's probably similar. I think the bandit attack is actually when you try to create a bigger history on an encode block, on an encode chain. Encode chains are the chains that are in the side of the main one, and the one that is the longest gets merged with the main one. And then I think people try to create a block that is longer to rewrite the history of previous blocks and then manipulate the chain this way. But I think it's different than this one because this one is about manipulating the price on the previous block. But it has similarity because I can see that it would be possible to create the bandit attack to manipulate the price of the difference between blocks. So I think it's similar, but not the same. Instead, Uniswap V2 adds this end of block price to a single cumulative price variable in the contract weighted by the amount of time this price existed. Add this end of block price to a single cumulative price variable. This variable represents the sum of the Uniswap price price for every second in the entire history of the contract. And the block price, just single cumulative price variable. Also, the V2 is already the one that gets stored. But I thought they said that it didn't store. Oh, I'm not really sure. So first block is 0, price 0, time lapse 0. Price is time lapse is the time between the end of a block and the start of the next. So guess the accumulated price times the time elapsed, which is the time between blocks. And that becomes the cumulative price. Starting price of new block is same as ending price of previous block. And then there's a time lapse again and changes the price. And it accumulates to the price cumulative. Okay, I think I get it. This variable can be used by external contracts to track accurate time-weighted average prices across any time interval. Because you divide by the time, I think. And then you have the overall. Yeah, but it's still a little bit unclear. Because in this case, it only went up, but what if it goes down? So I guess it only, because it's gonna be but it's not gonna be a negative value. It's just gonna, yeah, but I guess you have the average, so you're gonna have the movement anyway. This is done by reading the cumulative price from an ERC20 token pair at the beginning and at the end of the interval. Cumulative price from an ERC, so it takes the beginning and the end. The difference is this cumulative price can then be divided by the length of the interval to create a TWAP for that period. Yeah, how much it fluctuated during that period. I think I get it. Because you just are summing with the time as well. You multiply by the time, then you sum everything, and then at the end you divide by the time. So it gives you the fluctuation of the price. To calculate TWAP across the interval, check price cumulative and block times dot timestamp at the beginning and end of the interval. Maybe I think I'm actually gonna do this one because it's better to store this information. I didn't put the other one. No, I think I put swap. Yeah. 3. Calculates TWAP. Yeah, true. Yeah, block that timestamp. I'm also curious to see how they did the randomness, if they have randomness. But maybe they don't. because I know that randomness in the blockchain is really difficult to get, and I remember reading a bunch of stuff about it or watching videos about it. And at that time that I read, they were talking about that soon there's gonna be a better way to get randomness. So I wonder if that's already came out or what's the standard today for doing that. Because the blockchain is deterministic, so it's really hard to make random numbers. I guess this is enough for the thing. TWAPs can be used directly or as the basis for moving averages as needed. A few notes for a 10-minute TWAP, sample once every 10 minutes. For a 1 week TWAP, sample once every week. For a simple TWAP, the cost of manipulation increases approximately linear with liquidity on Uniswap, as well as approximately linear with the length of the time over which you average. Cost of an attack is relatively simple to estimate. Moving the price 5% on a 1 hour TWAP is approximately equal to the amount lost to arbitrage and fees for moving the price 5% every block for 1 hour. Hmm. There are some nuances that are good to be aware of when using Uniswap v2 as an oracle, especially where manipulation resistance is concerned. The white paper elaborates on some of them. Additional Oracle-focused developer guides and documentation will be released soon. In the meantime, check out our example implementation of a 24-hour TWAP Oracle built on Uniswap feature. The same that I had. Flash swaps, Uniswap. I think the rest I'm not gonna read for now, unless I encounter something on the V3 that forces me to. And it's better to just continue the V3 one because I just want to have an idea and then explore the project because it's gonna help me understand a lot better how it works, everything. That's my goal. Or maybe this is important to read so I understand better as I go through this stuff as well. Yeah, I'm gonna read that section and then I'm gonna close and go to the other ones. Just see if there's anything interesting, then go back to the Uniswap P3. I'll be right back. Alright, I'm back. Uniswap v2 core, the essential Uniswap v2 smart contracts consisting of this, which implements core swapping and liquidity provision functionality. Oh, this is for v3, but whatever. Oh, so the factory, as it is not, I guess it's a different design pattern. I think I've seen that before. Factory design pattern. I've seen it in videos, I think. Core is minimalist in design, removing all logic that is not strictly necessary to secure liquidity stored in its pools. Logic related to trader security or ease of use must be implemented in external helper contracts, since external helpers can be improved and replaced without needing to migrate liquidity. This improves on the flexibility and modularity of Uniswap. Uniswap Tier 2 periphery is an initial set of helpers including a router contract that performs the safety checks needed for safely swapping, adding and removing liquidity, a migrator contract that can remove liquidity from Uniswap v1 and deposit into Uniswap v2 in a single transaction, that library contract that can be used in the creation of other helper contracts. I wonder how this one is done, though. I guess on the V1 they probably have only owner functions with the modifier only owner that allow the person to if withdraw their funds. So they use that on V2 probably, but it's still interesting I think to see. An example or contract that creates a simple TWAP from Uniswap V2 cumulative prices. An example flash swap contract that withdraws the ERC20 tokens, executes arbitrary code, and then pays for them. Let me see, because it's easier if I can copy this stuff here. Okay. I think apparently it worked. Damn, it's impossible to read that better. Periphery contracts described as example are for illustrative purposes only and should not be used in actual transactions. Although this is a huge improvement, there are some new smart contract patterns introduced which developers building on top of Uniswap should be aware of. Core uses double if instead of if, wrapped if. Routers can convert between if and wrapped if, allowing users to use if directly. Core stores ERC20 token balances internally instead of relying on the balances stored in the ERC20 token contract. Core no longer calls transfer from or message.sender. Instead, the ERC20 tokens should be sent to Core directly by a router before calling the swap, mint, or burn functions. Core will determine the number of ERC20 tokens sent to it based on the difference between its current and stored balances. Core no longer returns the maximum number of ERC20 tokens for a given input amount. Instead, a router must specify the number of ERC20 tokens it wants. Hmm. Core will send this number as long as the invariant is preserved after taking 0.3% off any input amount. Routers should handle logic around slippage safety checks and multi-hop trades. Uniswap 2 contains many other significant changes and improvements, including the following. Smart contracts are written in Solidity instead of Viper. Use create to make the pool address deterministic based on the ERC20 token pair. Uniswap 2 properly handles missing return ERC20 tokens that do not work on Uniswap v1, such as USDT and oh my god. Built-in meta transaction approve function for liquidity token, increase reentry protection using mutax, adds support for ERC777 and other non-standard ERC20 tokens. Reentry protection. I think I'm gonna go to the next one. I think those are the ones that I read now. Yeah, read this. It's pretty much the same page, just navigating. I didn't read flash swaps, but maybe I'll do it quietly. Maybe I'll put some music here. This looks a lot like network OS. It's probably not though. Or maybe it is just the scale that is different. I think I'll try to read quickly the documentation here. Then I'll go back, I'll stop the music and go back to the V3 stuff. I think I'll leave it like this. I don't know how to. There's probably a way here with formulas to write it correctly, but it's not a big deal, I think. And this is fairly complicated here. Yeah, it's crazy. Yeah, this is crazy actually. Yeah, they thought about this. I mean, it makes sense, but I'm just gonna copy this. It's easier. Yeah, but it's still. They're saying that the core is reduced in complexity to prevent, not to prevent, but to maximize the chances that the liquidity providers are safe. But they're still subject, I think, for the to the router contract because the router contract has to have connection with the liquidity one. But I guess I understand what they're saying here. They're trying to reduce the complexity as much as possible for the component that actually has all the money, which is the core parts. This is important, I think. And now I have to see. I think I just do this. It's easier. Nice. I finally read all of that. Now I think I understand much better. I'll go back to this one. I think I'll go up to page 6 and then, or maybe 5, then I'll take a break to eat something. Maybe meditate a little bit. I'm definitely gonna finish this today. Well, depends on how hard the rest is, but I think I'm gonna finish today and then start reading the other stuff. Geometric mean price oracle. Uniswap v2 maintains two price accumulators, one for the price of token 0 in terms of token 1, and one for the price of token 1 in terms of token 0. Users can compute the time-weighted arithmetic mean of the prices over any period by subtracting the accumulator value at the beginning of the period from the accumulator at the end of the period, then dividing the difference by the numbers of seconds in the period. Note that accumulators for token 0 and token 1 are tracked separately since the time-weighted arithmetic mean price of token 0 is not equivalent to the reciprocal of the time-weighted arithmetic mean price of token 1. Using the time-weighted geometric mean price, as Uniswap v3 does, avoids the need to track separate accumulators for these ratios. The geometric mean of a set of ratios is the reciprocal of the geometric mean of their reciprocals. It is also easy to implement in Uniswap v3 because of its implementation of custom liquidity provision as described in section 6. In addition, the accumulator can be stored in a smaller number of bits since it tracks log p rather than p, and log p can represent a wide range of prices with consistent precision. Finally, there is a theoretical argument that the time-weighted geometric mean price should be a truer representation of the average price. Instead of tracking the cumulative sum of the price p, Uniswap v3 accumulates the cumulative sum of the current tick index. The logarithm of price for base 1.0001, which is precise up to 1 basis point. The accumulator at any given time is equal to the sum of logs 1.00 whatever p for every second in the history of the contracts. We want to estimate the geometric mean time weighted average price over any period. To compute this, you can look at the accumulator's value at t1 and at t2. Subtract the first value from the second, divide by the number of seconds elapsed, and compute this value to compute the time-weighted geometric mean price. Not sure if I think I understand the general points and the way that works, but the formula and these numbers, maybe not. Cumulative sum of the current tick index, which is precise up to 1 basis point, is equal to the sum of this. Okay, I think I got it. But I don't understand why is this 1 here at the end of the zeros there. Yeah, whatever. Liquidity oracle. In addition to the seconds weighted accumulator of log price, Uniswap v3 also tracks the seconds weighted accumulator of 1 divided by L, the reciprocal of the virtual liquidity currently in range, at the beginning of each block. Seconds per liquidity cumulative SPL. This can be used by external liquidity mining contracts to fairly allocate rewards. If an external contract wants to distribute rewards at an even rate of VAR tokens per second to all active liquidity in the contract, and a position with all liquidity was active from T0 to T1, then its rewards for the period would be R times L times this other stuff. In order to extend this so the concentrated liquidity is rewarded only when it is in range, Uniswap v3 stores a computed checkpoint based on this value every time a tick is crossed. as described in section 6.3. This accumulator can also be used by on-chain contracts to make their oracles stronger, such as by evaluating which fee tier pool to use the oracle from. This accumulator can also be used by on-chain contracts to make their oracles stronger, such as by evaluating which fee tier pool to use their oracle from. Implementing concentrated liquidity. The rest of the paper describes how concentrated liquidity provision works and gives a high-level description of how it is implemented in the contracts. Ticks and ranges. To implement custom liquidity provision, the space of possible prices is demarcated by discrete ticks. Liquidity providers can provide liquidity in a range between any two ticks, which need not be adjacent. Each range can be specified as a pair of signed integer tick indices, a lower tick and an upper tick. Ticks represent prices at which the virtual liquidity of the contract can change. We will assume that prices are always expressed as the price of one of the tokens, called token 0, in terms of the other token, token 1. The assignment of the two tokens to token 0 and token 1 is arbitrary and does not affect the logic of the contract, other than through possible routing errors. Conceptually, there is a tick at every price p that is an integer power of 1, this number. Identifying ticks by an integer index I, the price at each is given by this. So guys, this number is related to the tick interval. So the tick is determined by this number. That's why up there they use this number to get the geometric weighted mean. The sum of the prices, or I think it was the average or something like that, using the geometric mean. I guess I get it now. So this number is equal to the interval of the ticks they use, I think. This has the desirable property of each tick being a 0.01%, 1 basis point, price movement away from each of its neighboring ticks. For technical reasons, explain that in 6.2.1, however, pools actually track ticks at every square root price that is an integer power of this. Consider the above equation transformed into a square root price space. Okay. As an example, square root of p0 minus the square root price at x0. Oh, the square root at okay. So square root of p, the square root price at x0 is 1. Square root of 1 is the square root of this, and p minus 1 is this. When liquidity is added to a range, if one or both of the ticks is not already used as a bound in an existing position, that tick is initialized. Not every tick can be initialized. The pool is instantiated with a parameter tick spacing TS. Okay, tick spacing. Only ticks with indexes that are divisible by tick spacing can be initialized. Tick spacing. Instantiated with parameter tick spacing. Tick spacing. Spacing. TS. Small choices for tick spacing allow allow tighter and more precise ranges, but may cause swaps to be more gas intensive, since each initialized tick that a swap crosses imposes a gas cost on the swapper. Yeah, because you're trading more times, but you're getting more accuracy because it's more reliable. I think I understand. Whenever the price crosses an initialized tick, virtual liquidity is kicked in or out. This is good to write here, I think. I'm just doing this in case I wanna remember this stuff and not read the whole thing. So I think it's good to do this, even though most of these things that I do with writing this stuff on the open office and ended up not looking later, but I think it's useful. It's better to have it and not use it than to want to use it and not have it. The gas cost of an initialized tick crossing is constant and is not dependent on the number of positions being kicked in or out at that tick. Ensuring that the right amount of liquidity is kicked in and out of the pool when ticks are crossed, and ensuring that each position earns its proportional share of the fees that were accrued while it was within range requires some accounting within the pool. The pool contract uses storage variables to track state at a global per pool level, at a per tick level, and at a per position level. Okay, so it's tracking the state. It's kind of like React that you have use state and use context. So I guess maybe this analogy is correct, but maybe not. I guess the global level would be using something like using use context to store this information about all the pools at any given point, I think. Global states, or maybe a global variable is a better analogy. Global state. The global state of the contract includes 7 storage variables relevant to swaps and liquidity provision. It has other storage variables that are used for the oracle as described in section 5. Liquidity, global state. Price and liquidity in Uniswap each pool contract tracks the pool's current reserves, X and Y. In Uniswap 3, the contract could be thought of as having virtual reserves, values for X and Y that allow you to describe the contract's behavior between two adjacent ticks, as if it followed the constant product formula. Instead of tracking those virtual reserves, however, the pool contract tracks two different values, liquidity L and square root price. I think I'm following it, but one question that appeared in my mind is how is it possible that people can't create an unlimited amount of pools? Because maybe only the owners of the car contracts can deploy different pools, because otherwise what you could do potentially is create the pool, a different pool with the same tokens, and then direct people to that pool and manipulate these variables, but I'm not really sure. Also, well, if you could create a different pool, then what you could do is create a pool that is identical to a bigger one, but or maybe a smaller one, but with different prices, and then you can just do phishing attacks on people, so they send money to that pool instead of the other one, and then you arbitrage and make money off them. But I think they're probably only allow for people that own the contracts should deploy pools. This could be computed from the virtual reserves with the following formulas. L equals square root of xy, and square root of p equals square. So p is the price, and since the price is one reserve, one divided by the other, it's a little bit tricky. I remember it's kind of confusing to go from the reserves to the price. I think you need to do integrals, not integrals, differentiation between the amounts to get the price. It's a little bit more complicated to go from this formula to this one. Or maybe they are different. Yeah, but I guess they are connected, but they're not talking about the connection because this is probably the price. Yeah, square root price. Which would be p equals y divided by x. And then L is just square root of k. So I guess it doesn't they didn't change the formula that much actually. They just made it the real one, the virtual one equal to the square root of the initial one, I think. And this created the virtual reserves. Conversely, these values could be used to compute the virtual reserves. So x equals L divided by square root of p, y equals L times p, square root of p. Using L and square root of p is convenient because only one of them changes at a time. Price and thus square root of p changes when swapping within a tick. Liquidity changes when crossing a tick, or when minting or burning liquidity. This avoids some rounding errors that could be encountered if tracking virtual reserves. Yeah, with X and Y you have the reserves. So the difference is instead of storing the reserves, they're storing the value of the price in relationship to the reserves and the liquidity in relationship to the reserves. Because only one of them changes at a time. Don't they change simultaneously? Changes when swapping within a tick. Oh, I think I get it. Liquidity changes when crossing a tick. Hmm. Or when minting or burning liquidity. Yeah, so when you trade, but can't you move? Yeah, but if you move across ticks, then you're changing the liquidity. It's still a little bit confusing to me because I think they are related. I don't understand really well why only one of them changes within the tick. I think is understandable because the tick is the range for the liquidity to change based on the virtual reserves. But I don't understand when it crosses tick why the price doesn't change and the liquidity does. I guess it's because of the ratio stays the same, but and that doesn't make sense because the price is based off the ratios. When liquidity changes, should change the price. I don't understand that. Why they are saying it doesn't. Liquidity changes when crossing the tree. I think. I don't get it. You may notice that the formula for liquidity based on virtual reserves is similar to the formula used to initialize the quantity of liquidity tokens. Based on actual reserves in Uniswap feature. Before any fees have been earned, in some ways liquidity can be thought of as virtual liquidity tokens. Alternatively, liquidity can be thought of as the amount that token 1 reserves, either actual or virtual changes for a given change in square root of p. We track square root of p instead of p to take advantage of this relationship and to avoid having to take any square roots when computing swaps as described in section 6.2.3. The global state also tracks the current tick index as tick IC. A signed integer representing the current tick, more specifically the nearest tick below the current price. This is an optimization and a way of avoiding precision issues with logarithms, since at any time you should be able to compute the current tick based on the current square root price. Specifically, at any given time, the following equation should be true. So IC is the tick index. The global state uses this to track, which was what they were talking about previously. I don't know if this is a modulus, which means that this is always going to be positive, but I don't think that makes sense. But maybe it does. I think I'm just going to put log of square roots. It's a shame that I don't know how to do this square root symbol here, but I don't want to waste time on that. Times we will do this square roots of b. Each pool is initialized with an immutable value, fee y, representing the fee paid by swappers in units of hundredths of a basis point. Huh. It, uh, it also tracks the current protocol fee, which is initialized to 0 but can changed by unigovernance. This number gives you the fraction of the fees paid by swappers that currently goes to the protocol rather than to liquidity providers. Only has a limited set of permitted values. The global state abstracts two numbers, free growth global 10 and free growth global 11. No, 0 and 1. Yeah. This represents the total amount of fees. Maybe I should write this down as well. It represents the total amount of fees that have been earned by unit of virtual liquidity. Per unit of virtual liquidity. Over the entire history of the contracts. You can think of them as the total amount of fees that would have been earned by 1 unit of unbounded liquidity that was deposited when the contract was first initialized. They are stored as fixed point unsigned 128 by 128 numbers. Note that in Uniswap v3 fees are collected in the tokens themselves rather than in liquidity, for reasons explained in section 3.2.1. Finally, the global state tracks the total accumulated uncollected protocol fee in each token. Protocol fees 0 and protocol fees 1. This is an unsigned UINT 128. The accumulated protocol fees can be collected by unique governance by calling the collect protocol function. The global state tracks the total accumulated uncollected protocol fee each token. Global accumulated uncollected. So the fees are not collected. Hmm. Maybe I think I'll just copy this because I think it's important to study later. This I think is the same. No, FP 0. Yeah. Swapping within a single tick for small enough swaps that do not move the price past the tick. The contracts act like an x times y k pool. Suppose y is the fee, or gamma is the fee, i.e. 0.003, and y in as the amount of token 1 sent in. First, fee growth global 1 and protocol fees 1 are incremented. Okay, so it multiplies by 1 minus the fee. Delta y is the increase in y after the fee is taken out. Yeah, makes sense. Technically, the storage variable called protocol fee is the denominator of this fraction, or is 0 if 0. If you used the computed virtual reserves x and y for the token 0 and token 1 balances, then this formula could be used to find the amount of token 0 sent out. But remember that in V3, the contract actually tracks liquidity and square root of price instead of X and Y. You could compute X and Y from those values and then use those to calculate the execution price of the trade. But it turns out that there are simple formulas that describe the relationship between delta square root of price and delta Y for a given L, which can be derived from formula 6.7. So this is the relationship between the square root of price and the difference in Y by the trade, by the fees. There are also simple formulas that describe the relationship between this and delta X, which is almost identical, but the reverse for the price. And I think it makes sense because whenever you're trading is exactly the same thing, I think. If you're buying, I think you're multiplying, and then if you're selling, you're dividing. It's something like that, and that's why it's really confusing. Because it is so simple, but if you have a bunch of different trades at the same time, it gets really confusing about which one, the order of them, and which one multiplies, which one divides. It's really annoying to think about it, even though it's really simple. When swapping one token for the other, the pool contract can first compute the new square root p using formula 6.13 or 6.15, and then can compute the amount of token 0 or token 1 to send out using formula 6.14 or 6.16. These formulas will work for any swap that does not push square root of p past the price of the next initialized tick. If the computed delta square root of p would cause square root of p to move past the next initialized tick, the contract must only cross up that tick using up only part of the swap, and then cross the tick as described in section 6.3.1 before continuing with the rest of the swap. Initialized tick bitmap. If a tick is not used as the endpoint of a range with any liquidity in it, that is, if the tick is uninitialized, then that tick can be skipped during swaps. As an optimization to make finding the next initialized tick more efficient, the pool tracks a tick bitmap of initialized ticks. I think I'm gonna write this down. So it pretty much gets the initialized ticks, so it doesn't have to look all of them to see which one is next, I think. But it's kind of confusing. I understand everything, but not really well. I guess it will clarify to me a lot more once I get to the project and I see the code. And I think I'm gonna look at these a lot as I go through the project because it's probably gonna help me by visualizing what they actually done. It's probably gonna help me to understand the whole design of the thing. The position in the bitmap that corresponds to the tick index is set to 1 if the tick is initialized and 0 if it is not initialized. When a tick is used as an endpoint for a new position and that tick is not currently used by any other liquidity, the tick is initialized, and the corresponding bit in the bitmap is set to 1. An initialized tick can become uninitialized again if all of the liquidity for which it is an endpoint is removed, in which case that tick's position on the bitmap is zeroed out. Tick indexed state. I think I'm gonna stop here and go eat something. It's almost at the end already. There's still a little bit. Yeah, this is probably the best way. So I'm gonna watch these videos here while I eat. Not gonna. I'm gonna take off the headset and put earphones and watch these videos while I eat, and then once I'm done, I'm gonna go back and finish the documentation and then read all these articles here. I think I'm gonna listen to music while I read these ones and then read these ones out loud because these ones are gonna go slightly faster because I already read them. Just trying to get spaced repetition and a quick review. And these ones I never read before, so I might read out loud so I can pay more attention and understand better.
Welcome back.
So, I'll be right back.
Just wanted to talk to you today, give you an overview of DYDX, kind of talk you through our platform and our product, and then talk through our plans for layer 2 as well. So DYDX is a decentralized exchange for perpetual contracts, margin trading, and spot trading. In general, DYDX is a decentralized exchange that targets more advanced types of financial products that you can trade on cryptocurrencies. I'll go over what perpetual contracts are, what margin trading is, and then why you might want to use these products. But in general, DYDX is kind of targeted at more professional traders of cryptocurrency and traders that want access to these more advanced types of financial products. So first of all, why would you trade on a decentralized exchange? And then second of all, more importantly, why would you trade these more advanced financial products on a decentralized exchange in particular? This is probably pretty similar to why you might trade a lot of other types of products on a decentralized exchange, but in my opinion, especially trading collateralized products like derivatives and margin is especially important to do on a decentralized exchange for a couple different reasons. The first of all is that obviously trading on a decentralized exchange is non-custodial. This means that you remain in control of your funds for the entire time while you're trading. This is especially important for collateralized products like margin and derivative products where you have to keep your funds on the exchange for the entire time that you have a position open on these products. It's actually pretty different trading these kind of collateralized products on a decentralized exchange as compared to trading just more like spot or other types of products on a decentralized exchange. And the reason for that is when you're spot trading or you're just, spot trading is just a fancy word for just regular buying and selling. You can use a centralized exchange for that, and then you kind of deposit to the centralized exchange, make your trade, and withdraw back to your user-controlled wallet. You can't do that on derivative products because for the entire time you keep a position open on a derivative product, you have to keep your funds on the exchange or on the platform where you're trading that product. So, for example, if you have a position open on BitMEX or Bitfinex or something like that, you've got to keep your funds on BitMEX or keep your funds on Bitfinex or any of the other centralized exchanges you may use the entire time that you're trading that product. And obviously, while you have your funds on that centralized exchange, you're really exposed to potential hacks of the exchange, potential, there's instability in the exchange if the team runs away with the money or things like that, and you're just not exposed to the same types of risks on a decentralized exchange. The second reason you might trade these products on a decentralized exchange is it's much more transparent. So the operation of the entire exchange is transparent and auditable on chain. Obviously, very similar to other decentralized exchanges that are out there. But again, this is really important, especially for more advanced types of products, because it's not just trading that you're doing when you're trading these types of products. You're exposed to a lot of other different types of mechanisms, things like liquidations, things like how the collateral is held, all of that. In advanced products that you're trading, again, kind of similar to trading or the non-custodial stuff I was just talking about, is it's no longer a black box like you would have on a centralized exchange. And even if you can't read the open source smart contract code yourself, you can trust that there's a community of auditors, of more technically savvy people in the Ethereum community that are auditing a lot of these different protocols and are verifying everything that's going out there. And of course, UIDX has high quality third-party audits and everything like that as well. And then the last reason you might trade these products on a decentralized exchange is much more open. So users trade directly on a smart contract, which is open to anyone. Again, this is just kind of the ethos of DeFi in general, just building an entirely new parallel financial system that's open to many different people all over the world that they can all kind of come and trade on this one place together. So now, what are perpetual contracts? This is something you may have heard before. They're a little bit complicated, but they're actually not super complicated. I'll kind of go through what they are and how they work and why you might want to trade, or users in general might want to trade perpetual contracts. So first of all, they're synthetic assets. Synthetic basically means that the assets that are actually traded, they don't need to exist in the system. Only one collateral asset is required for the entire system to work. So that basically means for perpetual contracts, there's only one asset in the entire system. For DYDX, it's USDC. The only asset our smart contracts know how to deal with is USDC. But based off of this USDC, through the derivative mechanisms of the contract, you can kind of synthetically create all of these different assets you might want to trade. The other reason you might want to trade using perpetual contracts as opposed to just trading the assets directly themselves is because of leverage. So contracts can be traded with very high leverage. What leverage is it just multiplies your gains and your losses, of course. So always keep that in mind when you're trading with leverage. It's certainly a riskier way to trade, but it can also be used to really improve capital efficiency. This basically just means you could come to DYDX or any other exchange that offers leverage with, say, $1,000, and you can immediately start trading as if you had $10,000, say. And then the last reason you might want to trade with leverage is you can take long or short positions. Long just means you make money when the price goes up, and short just means you make money when the price goes down. So kind of getting back to the earlier point on synthetic assets, this is really cool, especially for decentralized exchanges, because one of the things a lot of different decentralized exchanges really struggle with is trading cross-chain assets. So you may have heard a lot of different talk about various cross-chain solutions that are out there to say bring Bitcoin to Ethereum or other coins to Ethereum or just other assets in general. They don't even necessarily have to be cryptocurrencies and to enable them to be traded on decentralized exchanges. Normally, the path for trading other types of non-Ethereum based assets on Ethereum decentralized exchanges is first of all they have to be represented as an ERC20 token or an asset on Ethereum. But this isn't the case for DYDX and this isn't the case for synthetic assets because it's synthetic and we don't actually need the asset within the system. Any asset can be traded, not just ERC20 tokens. Right now, DYDX has our main perpetual contract is a Bitcoin perpetual contract, but there's actually no Bitcoin anywhere in the system. So you can kind of trade this asset that doesn't actually exist in the system, which is great for decentralized exchanges. It just allows us to add many more assets much more quickly. The main kind of mechanism you need to understand if you're going to trade a perpetual contract is this mechanism called a funding rate. And this is really the core component of a perpetual contract. What a funding rate is it's kind of similar to an interest rate that you may pay if you're borrowing or lending an asset. But this is just a dynamic interest rate that is paid between those who are long the contract and those who are short the contract. I'm going to talk through how it works. But it's basically like sometimes those who are long are paying those who are short, and sometimes those who are short are paying those who are long. So kind of for the entire construction of the contract, basically what we want to create is we want to create this contract synthetically that tracks the price of another asset. So let's say we want to create a perpetual contract for Bitcoin. How do we ensure that this perpetual contract that we create is going to trade similarly or close to the price of Bitcoin? The way we do it is with a funding rate. So let's say the price of the perpetual contract is trading too high relative to the actual price of Bitcoin. So say Bitcoin is like $10,000 and the perpetual contract is like $10,100. So what you want to do is, in this case, of course, you want to drive the price of the perpetual contract down to trade at the price of regular old Bitcoin. But how do you do that? So the price of an asset goes down when people sell or when there's kind of less demand to go long and more demand to go short. So in this instance, you would make those who are long the contract, those who are making money when the contract goes up, you would make them pay an interest rate or pay this funding rate to those who are short the contract. And this would incentivize more people to sell and would drive the price of the contract back down to $10,000 in our example, or just the price of regular old Bitcoin. And it's dynamic because, of course, the price of the contract can change relative to the price of Bitcoin. Sometimes it may be too high, sometimes it may be too low. So sometimes longs are paying shorts, and sometimes shorts are paying longs. But this is really just the core component and pretty much like the only main component aside from liquidations of the perpetual contract that you really need to understand if you're going to trade it. And then kind of talking about the market for crypto perpetual products. Perpetual products are by far the largest market in cryptocurrency. So they're bigger than the entire spot market combined. So bigger than every other exchange that's just trading regular old cryptocurrency out there is the entire perpetual market. This is really currently dominated by the These are things like BitMEX, Binance, FTX, and a couple others, which are really big in this market. And then DYDX is a more recent entrant to the market as well. And then the last thing to mention is that perpetuals are not available to US customers on DYDX. However, spot and margin trading on DYDX are available to US customers. I'm going to read more about this online, but this is just due to a variety of regulations, especially around derivative products in the United States. So the next component to DYDX that is important to understand before we go forwards is DYDX is what's known as a hybrid decentralized exchange. Hybrid meaning that we have some decentralized components to the exchange and then some centralized components as well. The decentralized components are, of course, the open source smart contracts, which are running on Ethereum. This enables all of the great advantages I was talking about before in terms of non-custodial trading, transparent and open mechanisms for the exchange and everything like that. DYDX also has some centralized components to the exchange. So the central components that we host are the order book and then the matching engine. I'll kind of go through why we talk about this, or sorry, why we offer these order book and matching engine services in a centralized way. So the main reason we do it is because it's basically a trade-off for performance. So it allows us to offer much more performant trading on the exchange. So we can really approach or even get better than the performance of a centralized exchange while remaining non-custodial and transparent. Specifically, what I mean by performance, this is things like if you've heard of issues that decentralized exchanges have with trade finality. Trade finality basically just means when you make a trade on a decentralized exchange, normally you don't know what happens. Say if you're trading on Uniswap or 0x or something like that, you don't know what happens or what price you're getting until the transaction is actually mined to the smart contract. This is a pretty difficult user experience for a lot of different users, especially for more performance and more professional traders who really need instant trading. They need to know exactly what price they're getting. They need things like free and instant order cancellations on the order book, and a lot of these things are just really hard, if not impossible, to offer on a fully decentralized and fully open exchange. And then the last thing that it allows us to offer is a really simplified UI and then API as well. Actually, the API is really important. I'll go through that in just a second. But on the UI, again, with this kind of central order book and central matching engine, we can offer instant trade finality to our users. So this means when you make a trade on DYDX, you know what happened immediately. You know what price you got, you know what leverage you're about to enter into, all these different things. You know that your order isn't going to revert or isn't going to cancel, that kind of stuff. And then a lot of volume on exchanges actually comes from programmatic traders, as opposed to just users who are using the UI or the regular old website. But it's actually really important if you're building a decentralized exchange or any exchange for that matter, to make sure you have a really good API and make sure you have a really good experience for programmatic traders. One thing we've heard a lot from different traders, and especially more kind of advanced or more fund-based traders that are trying to enter into the decentralized exchange space, is that it's really difficult to get started. These types of traders are used to just trading on a centralized exchange. They're not used to, say, spinning up an Ethereum node or sending transactions to the blockchain, all these different types of things. But again, with our hybrid approach, we can offer a really similar trading experience to what traders are used to on centralized exchanges, specifically programmatic traders are used to on centralized exchanges. We have a great Python and great TypeScript client, and those just connect directly to our API. Okay, so going through a product demo now. So let's start here. So on DYDX, you can see it looks really similar to what you may have experienced on other exchanges before. And this is really intentional. Again, we're going after kind of the more performant, more professional types of traders who really want access to things like the order book over here on the left, seeing very advanced price charts, seeing very advanced statistics about their positions, which you can see on the center pane here. And then, of course, access to a lot of different order types. So here on the exchange, you can see all those different things. You can see the order books updating in real time. And then the next thing let's talk about is the different order types that are available on DYDX. So the first order type you can make on DYDX is a market order. All a market order is basically you just saying, I want to buy, say, one Bitcoin, and I'm willing to buy one Bitcoin at whatever the price of the market is at the time my order hits the matching engine. So it's kind of the simplest way to trade. A limit order is pretty much the same thing, but you get to specify the worst price that you're going to get as well. So you can say, I want to buy one Bitcoin at no greater than $10,000. And then if my order can't be executed, it'll just sit on the order book and I'll kind of wait for somebody to sell me one Bitcoin at $10,000 if that ever happens. And then DYDX also offers stop orders. Stop orders are a little bit more advanced, but they're actually really critical to trading more advanced types of financial products. So we have two different types of stop orders. So standard stop orders, this is basically you can just say, I want to exit my position or I want to place a market sell order for one Bitcoin if the price falls below $12,000. These are really useful for positions if you're not trying to lose money or if you're trying to stop your loss. So say you enter into a long position on Bitcoin when it's $12,000, and of course you think it's going to go up because you entered into a long position. But what if it goes down? Of course you're going to lose money. How much money you're going to lose? You potentially lose quite a lot if you get to the the point where you get liquidated. But a stop order, you can basically say, okay, I'm entering into this position at $12,000, but if the price goes down to $11,000, just sell my position and I'll cut my losses there. Trailing stops are a little bit cooler even because you can basically say, trailing stops are basically you enter into a percent. So you can say if the price of the contract ever falls by say 5%, then cut my losses and I want to get out. The trailing basically means that it will follow your position up or down as it goes. Okay, so those are the different order types. Let's go ahead and actually place an order now. We can walk through what that looks like. So there again on DYDX, main concept you have to understand is leverage. Right now I already have a position that's 4.15x levered. We could place different order sizes. If I'm buying, my leverage is going to go up. If I'm selling, my leverage is going to go down. You can also use the leverage slider here on the left to basically drag it to whatever leverage you might want to do. You can drag it to a long leverage, to a short leverage, just a really simple way to trade on the platform. And I'm going to go ahead and just place a buy order here to increase the leverage of my position to 5.4x. So I'm going to go ahead and place this order. Actually, sorry, going back a little bit. So one thing to call out here is that the fees on UIDX are fairly high still. I'm going to go over this and kind of our plans for layer 2 in just a second. But we'll come back to that. Of course, on UIDX, because it's a decentralized exchange, you have control over your trading on UIDX. This means you can sign orders directly on the exchange. What you're signing here is just, it's kind of similar to a 0x order. You're familiar with that. Just things like what assets you're trading, what price you're trading them at. And you can sign this with any different cryptocurrency wallet you might use. And again, so just stopping it right here, right after we place the trade. So this is kind of the performance I was talking about before. You can see here at the top of the order book on the top right, my trade immediately went through, it was immediately matched, immediately finalized. You can already see the status of the order in terms of that it's been filled. And then you can see the fill, you can see the exact price, and you can see the fee that you paid. Pending just means it hasn't been confirmed to the blockchain yet. So we won't go through all of this, but you kind of see with the remaining duration of the video. That's just the last thing to wait for is kind of the transaction to actually get mined to the blockchain. One other thing to call out is when you're trading on UIDX, you're not actually sending transactions to the blockchain. It's kind of UIDX and the central matching engine, which is sending trades on your behalf. It's kind of including those trades, the signed messages that you just made. But again, one of the limitations of UIDX right now is that you really have to wait for these transactions to get mined to the blockchain in order to see your entirely updated position. Okay, so let's keep moving. So a couple of limitations, we touched on these already. So just first of all, trading fees are high. That's just due to Ethereum gas fees. You'll probably experience this on any different decentralized exchange. But of course, this is a really big damper to trading on the platform for our users. Speed, the UI feels slow due to needing to wait for Ethereum block confirmations. We've had to wait for about 30 to 60 seconds for my transaction to get mined there. Margining, this is a little bit more financially complicated, so I won't go too much into it. But UIDX supports what's called isolated margining. Isolated basically means when you're trading on UIDX, you have to put down collateral for one specific product at a time. So say I want to trade both the Bitcoin perpetual and the Chainlink perpetual on UIDX. I have to collateralize my account 2 different times to trade both of those products. And I can't just use one pool of collateral to collateralize all the different products I might want to trade. And then the last thing is maximum leverage. So right now we offer 10x maximum leverage on perpetual contracts, and this is a lot lower than what you find on the centralized exchanges. On perpetuals, this is where you'll see the 100x's of the world. So our solution to this is layer 2 integration. Kind of our original approach to that is we're doing integration with Starkware. Starkware is one of the leaders for zero knowledge or specifically Star case rollups onto Ethereum. And I'll kind of talk about how our integration works with them in just a second. But first of all, let's talk about what are the advantages of doing this layer 2 integration with Starkware. So obviously, first of all, fees. Gas fees will be about 100 times cheaper on the platform. The savings will be passed on to traders, and this will really just mean that our fees will be very in line with what you'll experience on other centralized exchanges that you may trade on. Second of all, speed. So the UI is going to update immediately on trades. Funds will become immediately withdrawable. There will be no more waiting for transactions to mine, anything like that. So again, we'll be able to create a platform that, from a UI perspective, is every bit as good, if not even better, than centralized exchanges that traders trade on. Third of all is margining. Touched on this in the previous slide, but due to the increase in scalability, we'll be able to support what's called cross margining on perpetuals. All cross margining is, and it sounds a little bit complicated, but basically what it means is you just have one account on UIDX or one pool of collateral on UIDX. This will be used to margin any type of product you might want to trade on UIDX. So this vastly increases capital efficiency. So now if you want to trade, say, 5 different UIDX markets, you could use a lot smaller amount of capital to be able to do that. And this is especially important for market makers. So imagine you're a market maker on UIDX and you want to market make all the different products that UIDX offers. You'll have to, again, because UIDX only supports isolated margining right now, put down collateral for all the different markets you want to make on. And this just means it's really capital prohibitive for market makers to make a ton of different markets, because say UIDX offered 50 different markets, market makers would have to put down collateral 50 different times. Whereas with cross margining, they can just put down collateral one time and then just use that collateral to market make basically an unlimited number of markets. And this cross margining is basically what's going to allow us to launch many, many new markets in the near future. And I'll touch on that in a couple more slides. And then last of all, but not least, is much more performant oracles leading to much higher maximum leverage. So what we're doing with oracles is we're actually using the exact same oracle systems that we're using right now in Chainlink and then the MakerDAO 2 oracle system, but we're going to, instead of putting those oracles on layer 1 Ethereum, we're going to put the oracle prices on layer 2, the Starkware rollup. And this will decrease oracle latency. Latency meaning the time it takes from the price of the asset actually changing to the time that price change is reflected on the chain. It'll decrease that latency by about 100x. And it's hard for me to overstate. It sounds a little technical, but it's hard for me to overstate how important this is when you're operating a leverage exchange. And this will allow us to safely offer much higher maximum leverages. Okay, so let's go through how the Starkware integration actually works from a technical perspective. So the first thing that happens is kind of like we saw in our product demo just a couple minutes ago. You're on the UIDX website, or say you're trading programmatically through the UIDX API. First thing that you do is the trader cryptographically signs an order that they want to make on the exchange. Again, an order is just a cryptographically signed message that contains fields like what are the assets that you want to trade and at which prices. And then the first thing that happens is that order gets routed to the UIDX matching engine. And this is just hosted on our servers in a central fashion. So if a match happens, match basically meaning, say you're trying to buy Bitcoin and there's willing to sell Bitcoin at equal to or better than the price that you're willing to buy it for. So if there's a match, then the signed orders together are used to create the trade. And all the trade is just a combination of signed orders. So it's a combination of all the users that want to buy and then all the users that want to sell, and of course the prices have to cross. So what happens with this trade next is, before we actually get to Ethereum, and of course this is where all the scalability comes from, UIDX sends the trade that we're about to execute to Starkware, into Starkware servers. And what Starkware is basically doing is it's queuing a bunch of these trades together. So here's our trade 5, it's getting appended onto the list with all the 4 previous trades that I've done before. And then periodically Starkware will batch these trades together. Batching just means it puts a bunch of different trades in a group together, and then it will come up with a start proof for all these different trades. And this is kind of the magic sauce that Starkware provides. This is where the zero knowledge proving comes in, and it's basically just magic math that will translate this group of trades that we have into a Stark proof. And the really important thing about the Stark proof and where all the scalability comes from is the Stark proof is constant sized. And this sounds kind of magical. Basically, like you can prove a linear number of things or linear scale of things, and you can translate that into just a constant size proof. It doesn't matter how many trades are in the batch. There could be 1, there could be 1,000, there could be 1,000,000, and the Stark proof would be the same size. And this is where all of the scalability comes from. So, and then periodically, after these trades have been batched together, Starkware come up with a Stark proof for them. Then the proof is what's sent to Ethereum. And then what the smart contract knows how to do is the smart contract knows how to verify the proof on Ethereum, and then balances are immediately updated. We don't have to go too much into this right now, but another aspect of scalability is that balances are no longer stored directly in Ethereum smart contract state on chain. Because of course, say we had 1,000 different users trading in a batch, and we had to update the storage slots on Solidity for all the on fraud provers. So again, with optimistic rollups, one of the big things that
Layer 2 solutions for decentralized exchanges, or DEX. In addition to addressing privacy concerns and restoring decentralization to the crypto sector, DEXs also provide a sandbox for Layer 2 developers to play in. Scaling with the Ethereum network has been a persistent challenge. When the network becomes congested during high-demand periods, gas fees increase exponentially and transaction speeds grind to a halt. With Ethereum 2.0 in perceptual development, a number of DEXs have begun to experiment with integrating Layer 2 solutions to provide users who are willing to forego the Ethereum network with cheaper, faster options. Project Serum is probably one of the better-known success stories for a non-Ethereum-based DEX. The decentralized derivatives-based project is built on the Solana blockchain instead of the default Ethereum network that most DEXs operate on, but it is also fully interoperable with ERC20-based assets and Bitcoin. FTX CEO Sam Bankman-Fried and his team are the brains behind Project Serum, and according to Bankman-Fried, the project is designed to circumvent the privacy and safety concerns of centralized exchanges by giving users a permissionless method to invest with leverage and swap assets. The project also provides a cheaper alternative to the high gas fees and slow transaction speeds that frequently plague the Ethereum network during periods of high traffic. Technical issues such as congestion and high fees can make or break an investor. Bankman-Fried also agreed with Wintermute's claim that hardly anyone is using DEXs, as the vast majority of derivatives volume is on centralized exchanges, but he suggested that in theory, composability and self-custody should be incentives for more users to join the movement. While this is likely disappointing to investors, it at least provides developers some quiet time to focus on properly integrating Layer 2 solutions to DeFi protocols. The trend of major cryptocurrency exchanges becoming more centralized is unlikely to change anytime soon. This means that the first DEX to successfully provide a platform with low fees, privacy protections, and a fast user-friendly interface will rule supreme once investors make the choice to invest in decentralized finance and decentralized derivatives again.
Hello folks, today in this video, I'm going to introduce you QuickSwap Exchange, which is being created after fork the originator of automated market makers, Uniswap. But instead of supporting Ethereum, it supports Matic Network, which is a layer 2 chain on Ethereum, and supports fast and cheap transactions, which makes QuickSwap Exchange a next generation layer 2 decentralized exchange. If you don't know anything about Matic Network, I would suggest you to watch its overview video, which I created long back. Please click on the pop-up on top right corner to watch it. Even I have given its link in the description below. In this video, first we will talk about QuickSwap Exchange in brief, and we'll understand its tokenomics. Then we'll see how can we transfer Ether or ERC20 tokens from Ethereum mainnet to Matic mainnet. After that, we will see how can we trade and provide liquidity on this platform. And in last, we will farm quick tokens. Please watch this video till end so you don't miss out anything. And if you have not subscribed my channel yet, please subscribe and hit the bell icon for update. Now, without wasting any time, let's start. As I've mentioned before, QuickSwap Exchange is our next generation layer 2 decentralized exchange, which is built on Matic Network because of faster and cheaper transactions. And this is the main motive to create this video, because we all are struggling with high gas fee and slow transactions on Ethereum. And we will see in this video, when we do the same trade of ERC20 tokens on Matic Network, how cheap and fast it is. QuickSwap Exchange is fork of Uniswap because Uniswap is always professionally audited and has not been attacked till date. Even there is no change in the code except few cosmetic makeovers on user interface. But again, risks are same as we have on all platforms like impermanent loss, rug pulls, etc. So please do your own research before you provide liquidity and participate in yield farming. QuickSwap has its native token Quick, which is an ERC20 token on Matic chain with total supply of 999,992. From this total supply, 96.75% will be distributed to the community and 3.25 will be reserved for creators and advisors. Here's the complete bifurcation. 9% will be available for liquidity mining. So over the next 4 years after launch, quick tokens will be distributed via liquidity mining, split evenly among the applicable pools. 5% will be distributed to Uniswap Uni token holders. Users who are participating in Uni pools liquidity mining on QuickSwap Exchange will receive quick tokens as per their share from 5% of total supply. 3.25% will be reserved for creators and advisors to incentivize the curation of the platform. 1% will be distributed to Matic stakeholders. As of now, it is not decided yet, but it will happen when QuickSwap has reached a sufficient maturation stage and can handle the extra emission. And remaining 0.75% will be available for marketing to spread the word of QuickSwap to the wider crypto community and encourage the wider community governance of QuickSwap. Before we transfer ERC20 tokens or Ether from Ethereum mainnet to Matic mainnet, let's understand why there's a need to do that. So Ethereum is a layer 1 chain and Matic is a layer 2 chain. Ether and all ERC20 tokens are available on Ethereum chain. And QuickSwap Exchange smart contract is built on Matic chain. So we have to transfer ERC20 tokens or Ether from layer 1 chain, which is Ethereum, to layer 2 chain, which is Matic. To understand it more, I will suggest you again to watch my overview video on Matic Network. Its link is mentioned in the description below. As we just saw that we need to transfer Ether or ERC20 tokens from layer 1 chain to layer 2 chain, we can do this from Matic web wallet, which is wallet.matic.network. My MetaMask is on Ethereum mainnet and connected on this website. Here you can see on Ethereum mainnet I have around 800 Matics and 0.5 Ether. And on Matic I don't have Matic tokens but have 0.02 Ether. In this demo, I will show you how to transfer Matic tokens from Ethereum mainnet to Matic mainnet. Same process will apply to other tokens and Ether as well. By click on deposit, you can transfer Ether or related ERC20 tokens between networks. But here I don't see my Matic tokens to transfer. It's because I'm on Matic POS bridge. Let me switch it to Plasma bridge. Remember, to transfer Ether, you can use POS bridge as well. To know more about POS and Plasma bridge, I have given its documentation link in the description below. I've switched to Plasma bridge and now I can see my Matic tokens to transfer between networks. I'm going to transfer 200 Matic tokens for this demo. You can transfer any amount you want, but you have to pay gas fee for this transfer. And remember one more point. On Matic mainnet, all transaction fees are paid in Matic tokens only. But as transactions are cheap, so you can transfer few Matics and it will all depend on you. Again, if you want to stake Matic tokens, please don't transfer your Matic tokens on Matic mainnet. You need to stake them on Ethereum mainnet. Okay, click on confirm. If your Matic tokens are not approved, you may have to pay additional gas fee to approve them first. Transaction is till here, you know how you can transfer Ether or ERC20 tokens between networks and configure Matic RPC as well on MetaMask. Now I will swap some Ether for USDC stablecoin on QuickSwap Exchange. My wallet is connected and you can see that it is connected on Matic Network and I have around 236 Matic tokens and 0.01 Ether on it. So I'm going to swap some Ether for USDC tokens. In from field, change it to it and in to field, select USDC. If you don't see anything in the list, just click on select list. Now click on QuickSwap token list. You can see the list of all supported coins and tokens now. Putting 0.005 Ether and I will get around 6.6 USDC tokens. As my Ether is already approved, I am directly going to swap them and don't swap. Just see the gas fee. Too cheap. Click confirm again. Transaction submitted to the chain. Okay, swap is done. To see USDC tokens in your wallet, add its address in MetaMask. Farming rewards are going to over in that all tokens. As per the current value of my share, I will get
I just realized that I didn't do the Italian thing, and I also didn't do the Vim training. I trained some Vim off stream, but I want to do it more since I got the subscription. I want to make sure I really take advantage of it and that I still have time to train the other stuff as well, the terminal and the other stuff. So I want to spend a lot of time there as much as possible, obviously. So I think I'm going to start by doing the Italian thing. And then I'll go back to reading finish reading the paper, then then after I read the paper, I'm gonna put some music and train the stuff for maybe 20 minutes or something like that, and then after that I will read the other stuff. I think it was this one. Yeah.
Io,
Io,
I,
il suo,
il suo,
his,
che,
che,
that,
lui,
lui,
he,
era,
era,
he, she was,
per,
per,
for,
su,
su,
on,
come,
come,
as, like,
con,
con,
with,
loro,
loro,
they,
essere,
essere,
to be,
a,
a,
at,
uno,
uno,
one,
avere,
avere,
to have,
questo,
questo,
this,
da,
da,
from,
di,
di,
by,
caldo,
caldo,
hot,
parola,
parola,
word,
ma,
ma,
but,
cosa,
cosa,
what,
alcuni,
alcuni,
some,
è,
is,
quello,
quello,
that,
voi,
voi,
you, place,
o,
o,
or,
aveva,
aveva,
had,
il,
il,
the,
di,
di,
of,
a,
a,
to,
e,
and,
un,
a,
in,
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 noi,
noi,
we,
lattina,
latina,
can, of soda,
fuori,
fuori,
out,
altro,
altro,
other,
erano,
erano,
were,
che, quale,
che quale,
which,
fare,
fare,
to do, make,
loro,
loro,
there,
tempo,
tempo,
time,
se,
se,
if,
volontà,
volontà,
will,
come,
come,
how,
detto,
detto,
said,
un,
un,
an,
ogni,
ogni,
each,
dire,
dire.
tell,
I just realized that I'm taking 2 seconds and not one for each iteration because of the way that I did this. Oops. So I think I can just erase one of them. I'm gonna see which one is best to do that, so it's faster.
io,
Io,
I,
il suo,
il suo,
his,
che,
che,
that,
lui,
lui.
he,
Yeah, much better. I'm gonna leave it like this. Okay, back to this. Taking index state. The contract needs to store information about each tick in order to track the amount of net liquidity that should be added or removed when the tick is crossed, as well as to track the fees earned above and below that tick. Start, check input, fail, stop, swap within current interval. Is there a remaining input or output? No. Execute, computed, swap, and then stop. Yes, cross next tick. Okay, so it loops over and then until it stops. Actually, it doesn't loop, it just stops if the amount is enough, and then if not, they cross the tick. The contract stores a mapping from tick indexes int24 to the following 7 values. Each tick tracks delta L, the total amount of liquidity that should be kicked in or out when the tick is crossed. The tick only needs to track one signed integer, the amount of liquidity added, or if negative, removed. When the tick is crossed going left to right, this value does not need to be updated when the tick is crossed, but only when a position with a bound at the tick is updated. We want to be able to uninitialize a tick where there is no longer any liquidity referencing that tick. Since delta L is a net value, it's necessary to track a gross tally of liquidity referencing the tick. Liquidity gross. This value ensures that even if net liquidity at a tick is 0, we can still know if a tick is referenced by at least one underlying position or not, which tells us whether to update the tick bitmap. Fee growth outside 0, 1 are used to track how many fees were accumulated within a given range. Since the formulas are the same for the fees collected in token 0 and token 1, we will omit the subscript for the rest of the section. We can compute the fees earned by units of liquidity in token 0 above FA and below FB at tick I with a formula that depends on whether the price is currently within or outside that range. That is, whether the current tick index IC is greater than or equal to I. So this formula here. We can use these functions to compute the total amount of cumulative fees per share FR in the range between two ticks, a lower tick I1 and an upper tick IU. As FO or F0 needs to be updated each time the tick is crossed. Specifically, as a tick I is crossed in either direction, its F0 for each token should be updated as follows. F0 is only needed for ticks that are used as either the lower or upper bound for at least one position. As a result, for efficiency, F0 is not initialized. It thus does not need to be updated when crossed, until a position is created that has that tick as one of its bounds. When F0 is initialized for a tick, I, divided by conversion, is chosen as if all of the fees earned to date had occurred below that tick. Note that since F0 values for different ticks could be initialized at different times, comparisons of the F0 values for different ticks are not meaningful, and there is no guarantee that values for F0 will be consistent. This does not cause a problem for per position accounting, since, as described below, all the positions needs to know is the growth in G within a given range since that position was last touched. I think I'll stop less at this point because I'm probably gonna have to look at this sometime again, especially the beginning part. I feel like I understood everything, but this part, because I'm tired now, so I'm gonna try to go faster so I can move on to the other stuff that I want to study. Finally, the contract also stores seconds outside, seconds per liquidity outside, and tick cumulative outside for each tick. These values are not used within the contract, but are tracked for the benefit of external contracts that need more fine-grained information about the pool's behavior, for purposes like liquidity mining. All three of these indexes work similarly to the fee growth indexes described above, but where the fee growth outside indexes track fee growth global, the seconds outside the index tracks seconds, that is the current timestamp. Seconds per liquidity outside tracks the 1 divided by L accumulator. Seconds per liquidity cumulative described in section 5.3 and tick cumulative outside tracks the log 1p accumulator described in section 5.2. For example, the seconds spent above SA and below SB, a given tick is computed differently based on whether the current price is within that range, and the seconds spent within a range SR can be computed using values of SA and SB. The number of seconds spent within a range between 2 times T1 and T2 can be computed by recording the value of SR at T1 and at T2 and subtracting the former from the latter. Like F0 and S0 does not need to be tracked for ticks that are not on the edge of any position. Therefore, it is not initialized until a position is created that is bounded by that tick. By convention, it is initialized as if every second since the Unix timestamp 0 had been spent below that tick. As with F0 values, T0 values are not meaningfully comparable across different ticks. T0 is only meaningful in computing the number of seconds that liquidity was within some particular range between some defined start time, which must be after T0 was initialized for both ticks and some end time. Crossing a tick, as described in section 6.2.3, Uniswap v3 acts like it obeys the constant product formula when swapping between initialized ticks. When a swap crosses an initialized tick, however, the contract needs to add or remove liquidity to ensure that no liquidity provider is insolvent. This means that the delta L is fetched from the tick and applied to the global L. The contract also needs to update the tick's own state in order to track the fees earned and seconds spent within ranges bounded by this tick. The fee growth outside 0.1 and seconds outside values are updated to both reflect current values as well as the proper orientation relative to the current tick. Once the tick is crossed, the swap can continue as described in section 6.2.3 until it reaches the next initialized tick. Position indexed state. The contract has a mapping from user and address lower bound, a tick index, and an upper bound, a tick index, to a specific position struct. Each position tracks 3 values. Liquidity, fee growth inside, free growth inside 1. Liquidity L means the amount of virtual liquidity that the position represented the last time this position was touched. Specifically, liquidity could be thought of as square root of x times y, where x and y are the respective amounts of virtual token 0 and virtual token 1 that this liquidity contributes to the pool at any time that it is within range. Unlike pool shares in Uniswap v2, where the value of each share grows over time. The units for liquidity do not change as fees are accumulated. It is always measured as this, where x and y are quantities of token 1 and token 0 and token 1 respectively. This liquidity number does not reflect the fees that have been accumulated since the contract was last touched, which we will call uncollected fees. Computing these uncollected fees requires additional stored values on the position, fee growth inside last 0 and fee growth inside last, as described below. Inside last one. Yeah. Set position. The set position function allows the liquidity provider to update their position. 2 of the arguments to set position lower tick and upper tick when combined with message.sender together specify a position. I think I get it, this stuff here, just saying things that it was mentioned in the past, as just explaining how it works. 2 of the arguments just set position, lower tick and upper tick when combined with the message that sender guys specify position. So these are the arguments passed to the thing. So we need to specify which ticks are gonna be is the range of the liquidity. I think you understand. The function takes one additional parameter, liquidity delta, to specify how much virtual liquidity the user wants to add, or if negative, remove. Interesting. Makes sense, because, yeah, you have to specify the range and then the amount. First, the function computes the uncollected fees that the position is entitled to in each token. The amount collected in fees is credited to the user and netted against the amount that they would send in or out for the virtual liquidity deposit. To compute uncollected fees of a token, you need to know how much FR for the positions range, calculated from the ranges IL and IR, as described in section 6.3, has grown since the last time fees were collected for that position. The growth in fees in a given range per unit of liquidity over between times T0 and T1 is simply FR T1 minus FR T0, where FR T0 is stored in the position as fee growth inside 0 to 1 last, and FR T1 can be computed from the current state of the tick. Multiplying this by the position's liquidity gives us the total uncollected fees in token 0 for this position. So this is the formula. Then the contract updates the position's liquidity by adding liquidity delta. It also adds liquidity delta to the liquidity net value for the tick at the bottom end of the range and subtracts it from the liquidity net at the upper tick to reflect that this new liquidity would be added when the price crosses the lower tick going up and subtracted when the price crosses the upper tick going up. If the pool's current price is within the range of this position, the contract also adds liquidity delta to the contract's global liquidity value. Finally, the pool transfers tokens from, or if liquidity delta is negative, to the user corresponding to the amount of liquidity burned or minted. The amount of token 0 delta x or token 1 delta y that needs to be deposited can be thought of as the amount that would be sold from the position if the price were to move from the current price P to the upper tick or lower tick for token 0 or token 1 respectively. These formulas can be derived from formulas 6.14 and 6.16 and depend on whether the current price is below, within, or above the range of that position. Yeah, damn, this was a lot. I think I understand a lot better now than I did in the first time that I read this, like a lot better. But I'm still gonna have to look at this at some point, probably in the future. Or maybe not, if after I go through the project, it's probably gonna even make it more, it's gonna make it easier to understand, even more than was after reading all this stuff. Some parts of this were unclear to me. Relationship to this stuff of the reserves and the ticks, but I get the overall way that it works now. This thing here that was the part that was a little bit confusing, because I think up until this point, after this point, I started getting tired. So yeah, but I'm gonna put some music and train the shortcuts here. And then after that, I'm gonna read these articles. I think I'll put 10 minutes and then I'll put 10 more minutes if I feel like training more.
Tried so hard and got so far, but in the end, it doesn't even matter. I had to fall to lose it all, but in the end, it doesn't even matter. I put my
Everybody's moving in the back room. We're waiting for the sun to rise. Everybody's moving in the back room. We're waiting for the sun to rise. We move a little closer in the back room. Feeling deeper cause we know it's our time. Everybody's moving in the back room. We're waiting for the sun to rise. We move a little closer in the back room. Feeling deeper cause we know it's our time. We're waiting for the sun to rise.
So I'm gonna read the articles now while listening to this music. Just selecting some music.
I'm gonna see like a ship. I'm gonna see till I meet. I'm gonna see like a ship. I'm gonna see till I meet. I'm gonna see like a ship. I'm gonna see till I meet.
we're about to put the yellow paper. I'm gonna read some of it off stream and then some of it on stream. This is just too many pages, 41. But I definitely wanna read that. I think I'm gonna read right after I finish these articles here. Maybe tomorrow or some other time. Before I start reviewing this, probably. Yeah, I think I'm gonna stop here because I'm already really tired. And I don't think it's gonna be good. I'm not gonna be able to retain as much information if I continue going. Even though I want to keep going, I don't think I can concentrate. So I'm probably gonna go continue reading this off stream. I'm gonna give a break and then read off stream. And then the next, I don't know what I'm gonna do next when I come to record or stream. But I know that what I have in my mind next is to finish this and then finish these 3 articles here about zero knowledge proofs. Then read the Ethereum yellow paper. Then after I read the Ethereum yellow paper, I'm gonna go over the Uniswap project, all of the interface and all of the contracts. And then after that, I might study the governance and I might go back into doing these challenges here so I can. I'm not really sure if I'm gonna do this, but yeah. I'm particularly curious about the challenge 4 and challenge 7 because I want to know these things. And then after I study all that, I'm probably gonna go back to Rust and I'm gonna study the source code of the Polars library, which is the Python library for reading data frames in a more efficient way. And then I'm only gonna go back to trying to get data, which I think is not gonna be that hard once I have the hardware to do that. So after I'm done with all of this stuff, I'm not sure what I'm gonna do. So probably gonna go back to doing lead code challenges about graphs and trees, maybe, or I build something else that doesn't require a bunch of data. There's also a possibility. So yeah, see you next time.